my topic is all about allocating kernel memory. When a process running in user mode requests additional memory, pages are allocated from the list of pre-pages frame maintained by the kernel. This list is typically populated using a page replacement algorithm such as discussed in section 8.4. If a user process requests a single byte of memory, internal fragmentation will result as the process will be granted an entire page frame. So ito yung na-discuss sir last time about internal fragmentation. Yun yung sumusobra sa isang process, sa isang memory allocation. So, there are two types of memory allocator. Tawag sa kanila is body system and slab allocation. So what is body system? Body system allocates memory from a fixed size segment consisting of physical contiguous memory. Memory is allocated from the segment using a power of 2 allocator, which satisfies requests in unit size is power of 2. For example, if a request of 11 KB is made, it is satisfied with 16 KB segment. Bakit? Kunyari, ang initial memory niya is 256 KB. I-divide siya sa dalawa. At ang tawag sa division na yun is bodies. 2 bodies. Ang bodies left sa bodies right. So, i-divide siya hanggang masatisfy niya yung kailangan ng memory. Teka lang, nawawala ako. Kunyari, 256 yung start niya. So, kailangan niya i-divide yun para ma-satisfy niya yung 11 KB lang na kailangan. Tapos yung susobra dun sa... ang last niya is 32, di ba? So, pagka dinivide mo pa siya sa 2, hindi na siya pwede sa 11 KB. So, ito yung example ng physical contiguous pages ng body system. So, yung 256 KB, dinivide niya sa dalawa. Yung 128 para maging 2 bodies. Para masatisfy niya yung 11 na KB na kailangan lang. So, nakita niyo naman, di ba? Nakadivide. Tapos, ang susobra doon, yun yung papasok sa internal fragmentation. Pero ang internal fragmentation, gumagawa siya ng way para hindi masayang yung mga memory na yun. Ang slab allocation naman, strategy siya for allocating kernel memory. So alam naman natin ang kernel is an operating system. So siya yung nag-handle ng mga allocation. Is also known as slab allocation. A slab is made up of one more physical contiguous pages. A cache consists of one more slabs. Ang cache naman is, ito, meron ako dito. A computer memory with very short access time used for storage of frequently or recently used instruction or data. So, para siyang storage din sa computer memory or also known as cache memory. So, yung slab naman, ito yung mga lagayan. Kumbaga, ito yung mga sumobra na allocation. Ito, kunyari ito. Ito yung example. So, yung kernel objects, 3 KB objects lang. So, yung cache, pinapasa niya sa slabs, yung mga, sa physical pages, yung mga na-allocate niya. So, ang tawag sa objects na use, full. Ang sa wala namang laman or free, empty. Ang slab naman na meron siyang both ng use sa free objects, yun yung partial. So, no memory is wasted due to fragmentation. It is not an issue because kernel is a unique data structure that are associated by cache. Memory request can be satisfied quickly. The slab allocation scheme is thus particularly effective for managing memory. And then, the slab allocator first appeared in Solaris 2.4 kernel. Because of its general purpose nature, these allocators now also used in Solaris, saka sa Linux, originally used. Linux ang gumamit talaga ng body system.
I'm going to report about the memory map files. Consider a sequential read of a file on disk using a standard system calls open, read, and write. Each file access requires a system call and disk access. Alternatively, we can use the virtual memory techniques discussed so far to treat file input-output as routine memory accesses. This approach, known as memory mapping a file, allows a part of a virtual address space to be logically associated with a file. As we shall see, this can lead to significant performance increases when performing I/O. So ito palang memory mapping files, parang ito yung kapag sa isang software, halimbawa sa MS Word, pagka pinit mo yung menu na file, pwede ka mag-open, mag-read, tsaka write. Parang ganun, para mabubuksan mo yung mga save na files mo dun sa nakalagay sa hard disk mo. Working sets and page fault rates. There is a direct relationship between the working set of a process and its page fault rate, typically as shown in figure 8.20. Ito po yung figure na yun. The working set of a process changes over time as references to data and code sections move from one locality to another. Assuming there is sufficient memory to store the working set of a process, that is, the process is not crashing. The page fault rate of the process will transition between peaks and valleys over time. This general behavior is shown in this figure. A peak in the page fault rate occurs when we begin demand paging a new locality. However, once the working set of this new locality is in memory, the page fault rate falls. When the process moves to a new working set, the page fault rises toward a peak once again, returning to a lower rate once the new working set is loaded into memory. The span of time between the start of one peak and the start of the next peak represents the transition from the one working set to another. Next is basic mechanism. Memory mapping a file is accomplished by mapping a disk block to a page or pages in memory. Initial access to the file proceeds through ordinary demand paging, resulting in a page. However, a page size portion of the file is read from the file system into a physical page, or some system may opt to read in more than a page size chunk of a memory at a time. Subsequent reads and writes to the file are routine memory accesses, thereby simplifying files access usage to allowing the system to manipulate. Thereby simplifying file access and usage by allowing the system to manipulate files through memory rather than incurring the overhead of using the read, yung read command. Read tapos may ganun. So, para siyang method sa programming languages, ganun. And write system calls. Similarly, as the file is done in memory as opposed to using system calls that involves disk input-output files, access is much faster as well. Note that that writes to the file map in memory are not necessarily immediate or synchronous writes to the file on disk. Some systems may choose to update the physical file when the operating system periodically checks whether the page in memory has been modified. When the file is closed, all the memory map data are written back to disk and removed from the virtual memory of the process. Shared memory in Win32 API or Application Program Interface. The general outline for creating a region of shared memory using memory map files in Win32 API involves first creating a file mapping for the file to be mapped and then establishing a view of the map file in a process's virtual address space. A second process can then open and create a view of the map file in its virtual address space. The map file represents the shared memory object that will enable communication to take place between the processes. We next illustrate these steps in more detail. In this example, a producer process first creates a shared memory object using the memory mapping features available in the Win32 API. The producer then writes a message to shared memory. After that, a consumer process opens a mapping to the shared memory object and reads the messages written by the consumer. To establish a memory map file, a process first opens the file to be mapped with the create file method function which returns a handle to the open file. The process then creates a mapping of this file handle using the create file mapping function. Once the file mapping is established, the process then establishes a view of the map file in its virtual address space with the map view of file function. The view of the map file represents the portion of the file being mapped in the virtual address space of the process.
Edge.
Ito yung sample code niya. Cut mo muna. Papaliwanag ko. Post mo muna. That's our report.